Okay. Okay. What was, guys, what lesson first? Newton's law, is it?
Yeah.
Okay. Newton. Okay, let's see what this lesson was like. Yes. Oh. It probably would help if it was turned on. Probably. Okay. So the first question: what is the gravitational force between two masses of 1 kilogram which are 1 meter apart? So I would really hope that that one was okay. The answer is 6.67 times 10 to the minus 11 newtons. Because the m is 1, the m is 1, and the r is 1. So for this first one, the answer is 6.67 times 10 to the minus 11. In fact, you could use that as the definition of G. G is the gravitational force between two 1 kilogram masses 1 meter apart. So it's quite small. Okay, number 2. What about the gravitational force between two equal masses 10 to the power of 6 and 1 meter apart? So again, the formula will be like this. Down below is 1 squared, and on the top is 6.67 times 10 to the power of minus 11 times 10 to the 6 times 10 to the 6. 66 newtons, which is still problem. 66.7. Huh? Am I wrong?
No.
Oh, yeah. Okay. Now, yes, indeed. Even this is quite small, like 10 to the 6 kilograms. That's 1 million kilograms. So even if you have 1 million kilograms beside 1 million kilograms, 66 newtons doesn't actually seem like a lot. It's not really going to do much to the 1 million kilograms. You know. So again, the first two questions, the point I'm just trying to make is that it is a small force. It's actually a weak force. Okay, number 3. What is the velocity of the Earth as it orbits the Sun? Okay, so we'll need to use a circular motion formula. What one could we use? mv squared over r, because we can rewrite this to get the v. Now, there we go. F equals mv squared over r. So v would equal the square root of f(r) over m. But we know the formula for f. It's gmm r over r squared over m. Well, that's nice because that will cancel with that, and that will cancel with that, leaving me with just gm over r, which we know. I think I give you all the information here. 6.67 times 10 to the power of minus 11 times 29.74 kilometers per second. Happy? This one this looks okay to me, doesn't it? What the fudge? Is the power cable loose? Oh, it is. That's the problem. Okay, the next one is how far does a spaceship need to be from the Earth so that the total force acting on it from both the Earth and the Moon is zero? In other words, at what point will the force pulling it towards the Moon equals the force pulling it towards the Earth? And technically at that point the spaceship could just sit there and not be pulled either way. This projector smells like it's burning. That's probably a bad thing, right?
Oh, they died before the computer.
Yeah, this laptop outlives the projector. I don't like it. If it breaks, I just have to get another projector from the office. But I'm sure there's a little more life left in it. There, you see? A little life left. But it doesn't smell great. It smells like it's burning. Well, I'm sitting right beside it, beside the vent. Do you know what? You know what I think is? I think the fan is broken. You know, the fan that cools it down, because I don't hear it. You usually hear it go. So this will probably slowly heat up and explode. When it explodes, we might finish if we're still alive. Okay, but first physics. Let's see how much we can squeeze out of it. Oh yeah, so what's the force so that it cancels? Well, here is the Earth. Here is the Moon. Here's my spaceship. And this needs to equal this. Okay? So we'll call this distance x, and we'll call this one here r minus x. Where r is the distance between the Earth and the Moon. So we need g m1m over x squared to equal g m2m over r minus x squared. Cancel, 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 cancel. M1 r minus x squared must equal m2 x squared. Squared, yes. So we have, do you know what, actually, if I rewrite this a little bit, if I bring the m2 underneath this, actually, I can square root the three things here and get rid of that. So now I would have root m1 over m2 minus x root m1 over m2 equals x. M2x. No, sorry, not m2, just x, because I brought the m2 down. So now I can get my answer. X is, take that over, or root m1 over m2 over 1 plus root m1 over m2. Or maybe I should clean that up a little bit. Or times root over 1 plus root m1 over m2 m1 over m2. Just hit it on the calculator. Right, what's the distance between the Earth and the Moon? Sorry, go ahead, Monica. 3. Okay. And here we have a fraction, and here is a root and a 1 plus a root. And inside the root is a fraction, and inside the other root is the same fraction. Okay, what's the M1, the mass of the Earth?
5.97
And for the Moon?
7.34
So this is 5.97 times 10 to the, and then this one here,
22.
really? The Earth is that much bigger than the Moon?
Yeah, yes,
Let's make this kilometers. 347,000 kilometers. So what you got? Yeah, well, what did you get? It's not what I got. Okay.
Teacher,
Yeah.
this is the distance from
Centers.
the center. Do we need to?
Did I ask what exact? Did I say how far from the Earth?
How far does the space need to be from the Earth?
Usually we would measure these by center to center. If I did want it from the surface, I would have said surface. So I don't think I should subtract the radius of the Earth here. Okay, is this one okay? Next one? Yes. Who's this now? Come in.
Jerry. No.
Come on, Jerry. Come on. Come on. Come on. Come on. I'm sure you're just late because your sad Bruce isn't here anymore.
No.
No, say yes. What happened to you, Jerry?
Everything was late.
Everything was late, including you.
I woke up late.
Well, that was the first problem. You woke up late, yeah. The bus was late, yeah.
Traffic jam.
And traffic jam, okay, yeah. Right. What is the gravitational field strength due to the Earth on a plane which is 10 kilometers above the surface of the Earth? Okay, well, we'll just use our formula for G. What's that? G equals GM over R, isn't it? Over R squared, thank you. Okay, so what's the mass of the Earth? 5.24. Now, we have to add 10 kilometers onto the radius of the Earth. What's the radius of the Earth? So should this be more or less than 9.81? Less. The G on a plane, 10,000, thank you. Not 10 meters. Oh, thank you. Like this. Okay. 9.78. Slightly smaller value of G. Oh, the formula is the distance between the centre of the Earth and where you are. And I tell you in the question you're 10 kilometers above the surface of the Earth.
What is the unit?
You know the unit.
Newton per meter. Newton per kilometer. A kilogram.
Correct. Also, meter per second squared. The question? The what? Calculator. The calculator?
Yeah.
Alright. Yeah. Okay. Next one. how strong is the Earth's gravitational field if you're on the moon? So even though you're on the moon, the Earth is still having a pull effect on you. Although it should be quite weak, yeah?
Due to the moon on the surface of Earth.
Oh, sorry, the other way around. What is the gravitational field strength due to the moon on the surface of the Earth? So the moon is pulling on you. Also, the Earth is pulling on you, which is bigger. But what is the strength of the field caused by the moon? So if I go back to this formula, what do I need to change? Well, that's the mass of the moon, which is 22, and this is... Okay, and then the radius will be quite different. 22? Now, like this, isn't it? Now, I suppose last year when I did this question, I just used the formula for the distance from the center of the moon to the center of the Earth. But I suppose, since I did say in the question, what is the gravitational field strength due to the moon on the surface of the Earth, not the center of the Earth, I have two choices here. I'd have this one, or I'd have this one. But because I didn't tell you where you are on it, we should take the average. But if you take the average of the two, that's going to be the same thing as just the center. So, with good reason we'll use the center, even though I said the surface, because it will simply be an average. What? What? Use what? I didn't tell you where on the surface you were. On the surface of the Earth. It does, because if you're here, it'll be less, and if it's here, it'll be more.
But animals are always left surface, not in the center.
Huh?
Animals.
Yeah, are always here.
Yeah.
I know, but we don't know if we're here or here.
So I think.
So we'll use here. No, it's right. Because it's the average of the two. That's confusing. I don't understand.
Okay.
Right, what's the distance between the Earth and the Moon? 385,000 kilometers?
Yep.
So another couple of zeros, another 3 zeros there. So this should definitely be less than 9.81. Otherwise the Moon will be as strong as the Earth, which would have us floating. Indeed it is. Quite small. Stephen at Schnasche studying the Snoon. 33 micronewtons per kilogram is the field strength of the Moon on the Earth. Yes? Yes?
You gave us the difference between...
Totally radical. Awesome. Okay, continue. So, a rocket is fired into orbit slightly above the surface of the Earth and is breaking through the atmosphere. The engine is about to be cut off. How fast does the rocket need to be travelling so it can escape the pull of the Earth? So, we have a picture like this. There's a rocket here, and it's about to head out into space. If it's not going fast enough, it will just get pulled back down. But if it's going fast enough, it'll actually escape. So this is actually called escape velocity. Now I said it's slightly above the surface of the Earth. So what is slightly here? Well, slightly could be like 20 kilometers, 30 kilometers. In other words, I'll say that this distance here is roughly the radius of the Earth, although it's slightly more. What's the radius of the Earth? 6371 kilometers. So maybe it's 6391, but it actually doesn't really matter. Okay, so this here has two types of energy. It has kinetic and it has potential. When it's free, how much potential should it have? And we've talked about this many times. What's the potential energy for something that's freed? What is it?
Zero.
Zero.
But zero, gravitational force is extra, so how can potential energy be zero?
Essentially zero, nearly zero.
It's nothing.
Technically not, but I mean when it's a pico-newton, you know, or a pico-newton, do we really care anymore? Or femto-newton, something like this. Anyway, here the rocket only has kinetic energy. Now, we don't care how fast it's going if it's free, right? We actually just want it to be free. It could be going really, really slowly as long as it's freed. So in fact, we'll say both energies are zero. It's free, it's not really moving very fast, but it's free. It's not going to fall back to the Earth. That's the important thing here. So if this is zero, it means this is zero, which means this, minus PE. This is a half mv squared equals minus gmm over or. Well, that's nice because we don't actually need the mass of the rocket, it's not important. So the V will be 2gm over r square root. Yeah. Which we can type in. Okay, so 6.67 times 10 to the power of minus 11, and we said 6371000 times 2 times 5.9. $11.2 kilometers per second. Now, just to put that into context, (33 times the speed of sound? Dang, that seems really big. 11 kilometers per second. That is dang fast. Did I square root? Maybe I forgot the square root. That seems too big. No, I did square root. Wow, shocking. Is 10 to 24?
Yeah.
Whew, that's huge. Yeah, okay. Let's add on how many? 30 kilometers. You should be clear of the atmosphere after 30 kilometers. So we'll make this a 9. 11.2 still, if we round it off. So it wasn't really important that it was slightly above the surface. Even by 30 kilometers, it still needs to be going this fast to escape. That is frickin' fast. Now, I suppose, though, when we send spaceships up into space, most of the time, we're just trying to have it in orbit. We're not trying to have it escape the solar system. In fact, as far as I know, there's only one space probe that was sent out to escape the solar system to explore space. Voyager 2, I think it's called. Currently it's somewhere, currently it's just past Pluto. Because you might remember maybe 2 years ago, there was pictures of Pluto that were on the news. So Voyager 2, which began its journey in 70s or something, has made it to Pluto. So give it another 30 years and, give it another 100 years and it might make it to something else interesting. But I guess it has to be going this fast to escape the Earth.
get affected by the gravitational.
Yeah, I was just I was just going to say maybe it's not as bad as this because you just needed to be going fast enough so it could perhaps be caught by something else like the moon or Jupiter to pull it out. Because a lot of these things are planned on computers where they plan the path so that they could make use of as much pull from other planets. So perhaps Jupiter or the moon is pulling it out a little bit too, and can fire up a rocket to escape Jupiter as it's going by. So there would be a heavy use of computer simulations in this to plan the cheapest route that needs the least energy, so to speak. Okay, is this one okay?
Teacher, what is the R you use?
The radius of the Earth. But as I was saying to Monica, even if we add in the fact that the spaceship, I said, was breaking through the atmosphere, and even if we say it's 30 kilometers above the surface, it actually doesn't change this answer. 30 kilometers is not enough to affect this. What's 20? I added on 30, didn't I? Oh, I added on 20. Okay, well let's add on 30 then. 11.2 still. So even at 30 kilometers, it's still the same escape velocity. Yeah. Continue. Yeah. Okay. So that is Newton, and then SNASA next. SNASA.
All formula will be good.
Kepler's is not.
Oh.
What's wrong with you, Monica?
What's wrong with you, Monica?
What's wrong with you, Lee? Okay. Kepler now. Kepler. The one we did yesterday? Was it? Oh, yeah. Okay. From an observatory in, blah blah blah, estimate the mass of Mars. So we can use actually let me just draw a picture of what we have. So we have Mars, and we have a moon here, and I must give you the time here for the moon. What did I say it was? 7.65 hours. And do I give you the distance here? Zero kilometers. Okay, now what did Kepler say? Kepler said T squared equals 4 pi squared GM over GM or cubed, yeah. Now, what am I looking for first? The mass, yeah. So I can rewrite this as M equals 4 pi squared or cubed over GT squared. Right, so fraction time, 4 pi squared, thank you, times or cubed, 9380000. 6.67 times 10 to the power of minus 11 times something squared, 7.65 times 3600. So the mass of Mars is 6.44 times 10 to the 23 kilograms, yeah. B, speed of Phobos. Okay, so we could use this formula, F equals mv squared over r, which equals gmm over r. Yeah? Oh, we could use the, yes, I just realized the omega r one because we have the t, don't we? So v equals omega r, which equals 2 pi r over t. So that would be 2140 meters per second. Okay, C.
Teacher.
Yeah.
For A is the R center to center.
Yeah. It's center to center for the A, and same for B as well.
But it doesn't mention. I mean.
What do you mean?
9380 kilometer is from
It's center.
global center, but it doesn't say it reach Mars center.
Oh my God.
Okay, I will replace this with center to center then. Phobos radius can vary by up to 10%. What is its fastest and slowest speeds? So you have V1 or 1 equals V average or average equals V2 or 2. That, if I imagine it like this is when it's going, here will be going fastest, here will be going slowest. So I'll call this fastest, slowest, and then here is the average that I got a moment ago. Okay, so I said that the radius can change by up to 10%. So that would mean V1 would equal R1 over, or A over R1 times the average. Is that, I want to use letters so I don't get mixed up. I'll say V slowest will equal V average or average, and then over the radius slowest, it's when it's furthest away. So I'll write furthest to. Yeah, and I'll put numbers in a moment. And then likewise, V fastest would be R average, V average over R when it's nearest. Now, I said that the difference is only 10%. So this here would actually be 1.1 or average. And this one here would be 0.9 or average. So actually, I can get my two answers as 1 over 1.1 V average, and then the other one would be 1 over 0.9 V average. That is 10 over 11 times the V average, and that one is 10 over 9 V average. So these are the two speeds. So if I multiply this one by 10 over 11, 1945, that's the slowest it can be going. And then multiply it by 10 over 9, 2378. That is the fastest it can be going. Yeah. Next. What is the density of Mars? Alright. What one is this now? D. Density of Mars is its mass, which we know, over its volume, which we could know. Alright, so let's just hit that in. What do we get as the mass of Mars?
6.4
Thank you. And then that density is 4 over 3 pi r cubed. And in the question I would have told you 3390 cubed. So 3946 kilograms per meter cubed. So it's about four times denser than water. Should make sense. It's a rock after all. Yep.
I got 3940.
So?
Zero.
I don't know what you did to get to this.
Nothing. Well,
You typed in exactly the same numbers?
No, I think 6.43.
So then you have your answer. So what's your real question? So your real question is 6.43 okay? Because that's what you used.
Yeah.
So when I got my 6.44, Why did I get 44 and you got 43? Maybe because I typed in 3.1415 instead of the full digits, 3.141592654.
So everything is different. So if I
Well, no, because in the exam you only need to be right for the first three significant figures. 394. So, that's all I care about in the exam. If I see the first three are right, then it's good enough. Okay, E. What is the gravitational field strength on the surface of Mars? That is equal to gm over r squared. Okay, so 6.67 times 10 to the power of minus 11 times over so Mars is kind of like Earth, but it's not as big as Earth, right? So this should be a smaller value than 9.81. Yeah, 3.74.
So do we have to minus?
Minus. Oh, did I? No, no minus. Not yet, anyways. F. What is the altitude of the parking orbit? Or the probe? Now, what is a day on Mars? A day is 24 hours and 40 minutes. So the time is 24 hours.
Parking orbit. It's 24 hours.
No, 24 hours and 40 minutes to the parking orbit. We're on Mars, not Earth.
What? But the definition you gave us is
Yeah,
24 hours.
No, I said one day. Yeah.
Oh.
Yeah. That's right.
Teacher, number E
Yeah.
is on the surface of Mars, so
Yeah.
we have to minus.
No, you just said Mars.
Is 3390. What would you minus?
Oh, okay.
Okay. Continue? I don't know what you're saying. Continue. 24 hours and 40 minutes. That's 24.67 hours. I will in a moment. Right. Using Kepler. Kepler said T squared equals 4 pi squared r cubed over gm. And what do we want? We want the r. GMT squared.
Over 4 pi.
And what's this called, Sean? Cube root. Okay. Yes? I know, I need to subtract. I'll do that in a moment. 6.67 times 10 to the power of minus 11 times, what's the mass of Mars? Okay, times 24.666666 times 3600 over 4 pi squared. Now, this is the distance between the center of Mars and the probe. But my question was, what is the altitude? Altitude is the distance above the surface. So now I do need to subtract 3390000. Ah!
No.
Surely not. Oh no, I'm making a pig's dinner of this. Alright, hang on. There's something horrendously wrong. I must have forgot to put in the radius, did I? No, I did. Oh, the time is squared. Which I never squared the time. Okay, so this should be bigger now. Right, minus 3390000. And we'll make this kilometers. 17,082 kilometers
What?
for the altitude.
Maybe I'm
17.1 megameters. True. That's true.
What? Teacher, can you show me the calculator? The number you put in. What must I done now?
3.
What is the math you use?
This one okay? Too easy?
Oh, pi square. Oh, what? Pi square? Oh.
Yeah. I think NASA can have it.
You'll never work for NASA.
I wish.
Okay, continue.
Mm-hmm.
Yep. So, next. What is the gravitational field strength on the probe when it's in a parking orbit? Okay, so that's G equals gm over r squared. Right. 6.67 times 10 to the power of minus 11 times the mass of Mars, which we said is, thank you, 6.44 times, thank you, over, okay, 17082 plus, yeah, okay, 17082,000 plus 633. I'm expecting this to be quite small indeed. 0.10, oh, it's nearly 103. 0.102 newtons per kilogram. And finally, H. What is the total energy of the probe while it's in its parking orbit? Alright, so the total energy of the probe is its kinetic plus its potential, which is a half mv squared plus, well, minus gmm over r. Yeah. Now we need to figure out the v. So we have F equals mv squared over r. Oh yeah, we know the t, don't we? So that would be a half m 2 v equals omega r, so yeah, 2 pi over t r squared minus gmm over r. So if I just hit the whole thing in, right, did I probably say the mass was 100 kilograms, did I?
Yeah.
So 1 over 2 times 100 times, and then here's a fraction, 2 times pi times, and the radius is, yeah, what was it, 1, 2, 0, 0, 0, plus 3, 3, 3, 3. Okay, and the parking orbit is 24, yeah. Okay, so that's the kinetic part. Now time for the other part. Now I need the radius again. 1, 7. What's the radius? 000 plus. No, I ran out of space.
You forgot your square.
Well, it doesn't matter. I have to do this in 2 halves because I don't have enough space. Right, so first this is the kinetic part.
Square.
Thank you. You know, I won't bother because I'll just have to minus this part anyways. 6.67 times 10 to the power of minus 11 times 100 times, what's the mass? the fudge? Over. Did I? Right, so this is the total energy. I feel like it should be negative because it's still trapped, although it is, yeah, it is, although it's moving, it's actually trapped, so it should still be negative. Can we get this in megas? Yeah, minus 105 megajoules. So that's how much energy the probe would require to be freed from this circular orbit.
Stephen, if we didn't know the mass of probe, is there any way to know
The energy?
no mass of probe?
If I gave you this question but didn't tell you the mass of the probe, would you still work it out? I don't think so. I'd have to give you some other piece of information. You'll need to know the mass of the probe. Cannot think of any way to get it. No. You definitely need to know the mass of the probe or another piece of information about the probe. Yeah. If you knew something about its energy requirements or anything like that, perhaps. Yeah. Okay, did you write this down? Yeah. By the way, just so you know, I know this was one question and it was quite long, but it was one section B question. So I do say, you know, never do the field questions. The only time I would say there's an exception to that, you know, a nice gravity field question like this, I think, would be quite nice to do in the exam, because it's not really a field question, because half of it is circular motion and kinetic energy, so it's kind of like a semi-field question. But the field questions that involve magnetic fields and electric fields, students usually make a dog's dinner of trying to answer it. Yeah. Dog's dinner. Yeah. Okay.